Okay, having learned about dipoles, forces and torques in them, we are now ready to get into magnetic materials. Let me share my screen with you. Uh, let me share my screen. Share screen. Okay. All right. So this is lecture 7B1, magnetic materials. We'll talk about atomic magnets and bound currents, okay, from microscopic to macroscopic. In this course, we do not deal with microscopic so much, okay, just a little bit. For, uh, for magnets, the microscopic mechanisms is truly a discipline by itself. But we would be more focusing on how to connect the microscopic and the macroscopic description. So what happens when a material is placed in a magnetic field? Okay, let's revise to our question, what happens with E, with an electric field? If there is electric field and there are mobile charges in a conductor, okay, then you know the surface charges develop because the charges are mobile, they move to the surface. That's in a conductor, all right? Or if you apply an electric field and you measure the current, then of course it obeys Ohm's law. That is J is equal to sigma E. So sigma is the conductivity, okay, is the parameter, or 1 by sigma is resistivity. And that is the parameter which captures uh, that material property. But there are insulators which are no mobile charges, which are pure insulators. Okay, there we have seen either it polarizes. If you apply an electric field, then the clouds get distorted, and there is polarization, and you get dielectric. In fact, nonlinear dielectric, ferroelectric, and so on and so forth. Okay, but and the material property which captures this is the susceptibility or the relative permittivity, 1 plus chi e. Okay. So, and this I have not done, but we can easily do it. At one stage, I'll do it. That if you force a current through it, okay, through an insulator, then, and it is pure insulator with no traps inside, no imperfections inside, then you would get into a region called Child's law, that J is V square, okay, where conduction is by actual transport of charge from one side to the other, okay. So this is what happens with E, conductor and insulator. So, and it is the two material properties are conductivity and the susceptibility, electric susceptibility. Now let's ask the question, what happens with B? Okay, suppose I put a material in a magnetic field. Now that depends on what are the magnetic dipoles, how do magnetic dipoles respond inside the material? Do they get induced, or are there already dipoles, okay, and they react to the magnetic field? And what is the origin of this magnetic field? In very brief, we have already seen spinning electrons, okay, and the electrons need not spin only, they also orbit around the nucleus. So orbiting electrons, there could be already permanently magnetic dipoles like in iron, nickel, and cobalt, the famous three. So that could be existing magnetic dipoles. So we know that magnetic field is because of current, moving charges, because of some current. Okay, but this moving charges around in an orbit is also a current that we have seen. And so what happens? So there are materials in which this oppose the applied field weakly, and they are called diamagnetic. We'll describe it a little bit more later. Or initially they're not ordered, they're there in the material, but they're not ordered, especially the electrons, okay, the spinning electrons. And but once you apply a magnetic field, then some weak ordering of that happens, and that is called paramagnetic. Okay, and there would be existing dipoles, very strong dipoles, and they would order, and that are the class of materials like ferromagnetism, ferrites, ferrimagnetism, antiferromagnetism, I'll briefly describe towards the end of this chapter in the next section. The question to ask is, which material property captures this response? Okay, of course, the answer is similarly like electric susceptibility will have a magnetic permeability, okay, or magnetic susceptibility. All right, so that is the brief thing that we want to do, but we will like to concentrate on description, macroscopic description, not at the dipole-dipole interaction level in the material. Okay, so let's look at the atomic orbits. Okay, that is one of the, we have already seen the spinning electron, and we said spinning electron, in fact, it's called, this quantity is called one Bohr magneton. Okay, and quite often the magnetic properties are described in terms of how many Bohr magnetons are the dipoles that are inside. Okay, and is the value which we know is in terms of energy per Tesla, EV per Tesla. So spinning electrons is one source of magnetism in the material. The other source is really electrons not only spin, but also orbit the nucleus, the orbital dipole moment. Okay, so let's say the electron is spinning like that. So the current is, of course, the conventional current is in the opposite direction, and because of that, the the magnetic moment is in the minus k direction. Okay, so this is the orbital dipole moment. Now this is already existing. Suppose it is going around the nucleus like that. Okay, now we apply a magnetic field. What happens? That's the question that, okay. So what is this m? You can always calculate E by T. It is such a short time period that we actually can think of it as like a steady current. And we know this, okay, by E omega 2 pi by omega, and this is V by R. R is the radius. So once we know current, then the magnetic field is m I pi r squared. That should have been a k cap here. Okay, so m is equal to minus half. I just plug in the values of I here, and I get minus half EVRK. So this is, remember, this is minus, that is k direction is this, and this is the minus k direction because electron is negatively charged. All right. So now I'll place it in a magnetic field. It experiences torque, but this is a huge, this orbit is quite large, and so it is harder to tilt the whole orbit. But there is something more significant that happens. Okay, that is, this velocity gets changed, okay, because of the applied magnetic field. It is pretty hard to change because the torque, the whole orbit. So that is one effect, but it does happen, but it's very little, okay, or can be almost neglected in most cases. But the change in velocity is there, which is significant. Okay, so think of it as now applying. Okay, this is going around E. This is the nucleus plus E, and it is moving around E, and I apply a magnetic field. What happens to the change in velocity? Once change in velocity occurs, then you remember that the magnetic dipole moment depends upon the velocity. Okay, so change in velocity would also mean that there is a change in magnetic dipole moment. Okay, so that is what we'll estimate. So the orbiting electron speeds up or slows down depending on the orientation of B. Okay, so if you do in the reverse, it will it can be the reverse. But let's look up. So what is the why is it? Of course, there is centripetal force, and centripetal force is MEV square by R, and this is the electrostatic force. Electrostatic force gives you the centripetal force. Now, on application of the magnetic field, okay, we have now added to the centripetal force E V cross B, right? So V is this, so V cross B, and it is for minus E, so it adds up, right here. Okay, so it adds up to the so now I have indicated the change velocity as V prime, MEV square by R. This is the electrostatic, and this is the magnetostatic. All right. So let's make an assumption that, so I can always calculate E prime V as mv square in the earlier v. All right. So EV, this term, I'm now looking at this term because that's the term which really controls the magnetic moment. Okay. So V. So how much is the change in the velocity V prime? Okay. So MER V plus V, V minus V, and then I make an assumption that this is not magnetic field is not so much this force that there is a change in the radius of the orbit. The radius of the orbit is roughly the same. Okay, let's assume it. Let's take it to be that. More justification can be given, but let's take the radius to be the same, and we know that this is going to be small. V minus V is a very small effect. Magnetic field is a small effect. So assume delta V is small and R does not change. And in that case, I can calculate delta V because I know, okay, so V prime is almost equal to V, and hence delta V is EBR by 2ME. All right, once I know delta V, I can always calculate the change in the orbital speed, uh, means change in dipole moment M. And hence I go back to this and I say my delta M is, instead of V here, I put delta V, and I know it's in the minus direction. So the change in dipole moment is opposite to the D that is given, right? So it opposes the applied field. So delta M is opposite to the direction of B. That is, change is anti-parallel to the field, and this is indeed the origin of diamagnetism. Wherever there is an electron moving around in an orbit, okay, there would be wherever, and is there everywhere in all materials. So it's almost like universal, okay. But it's a small effect, okay. From the assumptions that I have made, you can make out that for the typical fields that you can apply, and for the typical values of the electron values and the velocity, this is a small effect. So it's a weak effect, and but shows up. But if there is no other magnetic field, then this is the only effect, and then it shows up. So most materials that were called diamagnetic are the origin, microscopic origin lies in this. How it changes with other things like temperature and all that were microscopic. We are not considering this. I just wanted to give you a brief idea of the origin of diamagnetism is because of the change of speed of the circulating electron in an orbit. That idea comes through this. Okay, so these are atomic orbits. So there are two sources. One is source of paramagnetism, spinning electrons. Okay, then they get ordered if you give a magnetic field. There are spinning electrons with both plus half and minus half in all directions. But if you apply a magnetic field, then the plus and minus, if they're free electrons, they align and you get a net magnetic magnetization. All right. Okay, so let's call it, what is all this giving rise to? If we apply a magnetic field, it's macroscopically, let me introduce to a new macroscopic variable, which is M, okay, vector, which is analogous to the polarization P vector that we had seen in electrostatics, obviously. So let's just define it, okay. So matter can have magnetic dipoles. I've given you two sources, there can be more, and they can get induced or ordered. A magnetic dipole can be induced, okay, because something starts rotating because if you have applied a magnetic field because of the torque, or ordered, they're already existing but randomly, and they get ordered by application of magnetic field, and so those dipoles will lead to magnetization. That's the whole point. So, and we know the paramagnetism, dipoles associated with spins of unpaired electrons. Okay. So the torque tends to line them up parallel to the field. Okay. Whereas in diamagnetism, the orbital speed of electrons get altered, and there is a change in magnetic moment, and that is anti-parallel to the field. Okay. So I've just summarized what I was doing in the previous slide. Okay. Now the state of magnetic polarization, there's a state vector in some sense. Okay, is quantified by, so we define M vector to be the magnetic dipole moment per unit volume. Okay, so it is a macroscopic but per unit volume. All right. So, and I can define it that if I take a small delta tau, the volume going to zero. So if I add up all the dipole moments, okay, and then divide by the small and take its limit to the volume element, and the unit is of course amperes per meter. So that is the new macroscopic variable that we'll be dealing with in this chapter a lot more. Now, before I go and deal with, and I'll require another fundamental theorem. We have done two theorems last class. So I'll do another fundamental theorem, corollary 3. So this is useful in my next derivation. So let's look at this. This is, we know already the Stokes theorem, okay, and we know divergence theorem. Okay, it's sort of a mixture of that. Okay, that is the curl. We in Stokes theorem we know that the curl of on a surface takes it to this boundary, and it is a line integral of the boundary of the surface. Okay, here it is the curl of a vector function, but over a volume. Okay, and that will take it to the surface. Okay, so V cross dA. So take the curl and integrate over the volume. That is same thing as take the boundary of surface of that volume and the bounding surface of that volume, and take its cross product with V. All right. So, and that is the fundamental theorem. Okay. So, in many of these theorems, what is to prove, the proving technique is to define as a constant vector C. Okay. And this looks like divergence theorem, and this is about curl. So, what you do is take a new vector, define a vector V, which is cross with a constant vector. All right, so let's do that. And then I use divergence theorem. So because it looks like divergence theorem, okay, so this divergence theorem, okay, divergence. Now instead of the vector function, I say that V cross C tau, okay, and that we already know. Okay, so if it is divergence theorem, then it is V cross C dot dA of the surface. Okay. Uh, I can, so this is of course I could write down in terms of C cross V, but I've written down, and that is it picks up that minus sign. All right. So just defining this V cross C in divergence theorem. That's what I've done. But there is a product rule. So I'll apply, this is del dot V cross C. So I'll use the product rule. Okay, del dot V cross C, I can write down as C dot del cross V minus V dot del cross C. This is by the one of the product rules you are by now you are familiar with. But C is a constant vector. So what is this quantity? This is 0. Okay, the cross product, the curl of a constant vector is 0, and hence this quantity is nothing but C dot del cross V. Okay, the curl of the vector function itself. And this one, V cross dot dA, is a identity, vector identity cross with, so A cross B dot C. Okay, and hence I can put it in the form such that I get V cross dA. Okay, so I'll use this of course, but let's look at this also. Okay, so dA dot V cross C can be written as minus C dot V cross dA. It's just a identity. Okay, so that I got my right hand side by minus C dot V dA and my left hand side by C dot del cross V, and that is the actually the proof. So C dot del cross V d tau, I have just used that. Okay, so del dot V cross C d tau is nothing but C dot del cross V. Okay, and V cross C dot dA, I write it as minus C V cross dA. All right, so and then I take C cross V is minus C, that this minus, that not this minus I picked up from here. All right, so that proves the theorem. So how do you remember this theorem? This is the curl of the volume. So it has divergence origin, but it is about the curl. Okay, so volume to the surface area. Okay, so if you take the curl, then it is the V's cross product with the differential area integrated over the surface. Okay, So that is the corollary that I'd like to use in the next slide. All right. So, and then from here, of course, you can prove that any of this seawater, this could be ijk. So each component would be true. Okay. If a constant vector is, for example, in Cartesian coordinates, it's ijk, and hence this would be for each component it is true, then of course it is true for the whole identity. All right. So that is the proof of the theorem. All right. So now we are interested in the field of a magnetized object, okay, bound currents. You remember in electrostatic also did something. The field, the electric field due to a polarized object. Okay, so this is the counterpart of that. The field of a magnetized object is the bound currents. The derivation is also going to be similar, and you'll see that there is a parallel. All right. So let's go through it. For here, of course, we know the dipole, um, the vector potential because of a dipole, and this is r, and I should have a volume element d tau. So what is m? If I a volume element d tau carries a dipole moment of m is per unit volume into d tau prime, this is source, right? And hence think of it like this is my chunk, my magnetized object, and this is the difference element, and this is m d tau. So that is, let's say, pointing in this direction, and r is the field vector from the source. All right, and so I can, so this is the potential due to this m d tau. So m is the magnetization, okay, and m into d tau is the total dipole moment of this differential volume. All right. So the total vector potential then I can write down now by integration. Okay. So a dipole of r at the, okay, is of course mu naught by 4I. Instead of m, I write down m r star d tau prime cross r by r square. Okay. So then of course, since I know now that is with respect to the source coordinates, that is only here, 1 by r is r by r square. We know this. All right. So that is, we have proven this many times. So that is r hat by r square, and hence I can now convert that into a gradient of 1 by r. And then, of course, you know the theorems we can apply. All right. So I do that. I convert r hat by r square to the gradient with respect to the source coordinates of 1 by r d tau prime. Okay. Remember, this is the plus because it's so with respect to the source coordinates. So now let's we can integrate this by parts, okay, because this is a differential and this is a vector. So the corresponding rule, the product rule is, if you take del cross f of v, then we have this quantity now. Okay, that is the vector, which is the magnetization. Okay, cross the gradient of f, okay, and f is here 1 by the 1 by curly r. All right. So we can now use integration in parts by representing this as this minus this. Okay, that's all I do. Okay, so I write down this. This is, okay. So 1 by, all right. So this quantity, okay, that's minus because it's minus is minus, and this quantity, this is printed here. So 1 by r is the f, okay, del cross m. This is the 1 by r del cross m, and this is the minus of del cross the vector function into f mr by beta. So it's a simple integration by parts coming from here to here. Now I'll invoke the fundamental theorem I proved just now. All right. So what was that? That if it is del cross V, then I can replace it by minus B cross dA. So this is now a quantity which is now waiting to be applied this corollary, right? So del cross this, okay, is will be that, okay. So we can now write down So the first part, the second part, of course, is minus minus becomes plus, and this mr by dr by a. So we use that. All right. So invoking that fundamental theorem. Okay. So now we have two quantities, and remember, in both quantities there is some quantity. Okay, this is the potential. There's some quantity by r. R is this distance between from the source to the field point, and this is also a current divided by r. Okay, so and that looks like the potential, a current divided by r, a current divided by r. So that just requires interpretation. Okay, so now we can, so I'll write it down in that form so that I can interpret it that way. So there is a quantity divided by r over the volume, and there is a quantity divided by r over the surface. All right, so dA, of course, I can represent it with by dA prime and the n vector which is perpendicular to that area, right? So that vector can be represented. So this is a quantity divided by r integrated, a quantity divided by r integrated, and that looks like that we can define this quantity as a current, and that we call as the bound volume current, which is del cross m. Okay, so this is the source, but okay, so this del cross m, and then this is the surface. Okay, so this can be represented as a surface current, which is the bound surface current, which is m cross n. Okay, so dA prime I have taken out, and n I have taken, so m cross n. So this, the dipole potential, the vector potential of dipole for a magnetized object can be represented as as the two contributions. Okay, one is from the volume bound current and the surface bound current, if there are any. All right, so let's rewrite in that form. So the vector potential is bound current divided by r d tau prime, and bound volume current, and the bound surface current over the whole surface. There are two contributions in general can be. That's convenient. Okay, and so these two definitions are important. In other words, find the equivalent volume and surface bound currents, okay, to obtain A, and once you know A, you can get B. Del cross A is B, and hence it is important to realize that for a magnetized object, we can replace it by the corresponding equivalent currents, which is a volume current del cross M, and the surface current, which is M cross M. So this sounds very similar to what we had done in electrostatics. And what is that? So in electrostatics, compare. So the bound charge was minus del dot P. Of course, everything in magnetism becomes cross product. So of course, there is a minus here, minus del dot P. And sigma B, the bound surface charge, was P dot M. And this is M cross M. Okay. So there is a very pleasing symmetry between electrostatics, the polarized object, and the magnetized object. Okay. So what we did, we started with the for a dipole, then we considered a small dipole element, integrated over it, uh, used integration by parts, used the corollary to change from the volume to surface, and found that there is two components. One is the bound volume current, and one is the uh, bound surface current. Quite easy, but very useful. So these two formulae, of course, will guide your problem solving. So the idea of bound currents, let's look at this is mathematical definition, but sometimes important to view it physically in however hand waving way, then it gets the mathematics gets into the inner being, okay, into the bloodstream, so to say. So let's look at the idea of bound currents arising from M. Okay. So mathematically it is rigorous, there is no point, but let's look at, so consider a thin slab of, this is a thin slab of uniformly magnetized material, okay, initially. And the dipoles here, each dipole is shown by a tiny current loop here, II, tiny current loop here. All right. So this, and the magnetization is is pointing in this direction, and this is the thickness T. Okay, and if you look at only a small chunk differential element, okay, of this dipole, then it will look like there is a current going around that, and magnetization is, and area is A here, and thickness is T. Okay, this is what this is actually composed of. All right. Now, uh, so you can see that all internal currents is side by side. So there is a current going here and this current going here, so they'll cancel. Okay, so all internal currents cancel. Okay, so that cannot be any, because it is uniformly magnetized. Okay, since there are all internal currents cancel, so there is no JB, there is no volume current inside the material. Okay, so I del cross M is equal to 0. That is, M is anyway uniform everywhere, so del cross M is 0. So that only means physically that all the internal currents of each of these little loops cancel. Okay, but they don't cancel at the edges though. Okay, so they only survive at the edge, because once it is at the edge, there is no adjacent to kill it. Okay, and hence the whole current situation would look like as if all the edge currents survive, as if the edge current is flowing like a ribbon. Okay, and the edge is flowing in this direction. Okay, each one is actually bound. Okay, but in net wise they're all uncompensated, so it looks like the current is flowing in this direction, and that is M is in this direction, and for this surface N is in this direction, and hence KB is M cross M. All right, there is no volume current, but that can be a surface current. Okay, whereas M is in this direction and is the perpendicular to the surface N. All right, so remember that all moving charges are bound. There is no free current, but it's like a free current. Okay. Their origin is in little bound currents. So all these bound currents give rise to this surface current. That's the physical picture that comes up. That's what I wanted to. Okay. Now let's look at a little less for a quantitative. This is a qualitative feeling, but let's get to the quantitative feeling for this, and that is take a differential element. It is pointing in the M is pointing in this direction. So of course this is equivalent to the current going around this, right? So let's look at, so what is the total magnetization? That is A is the area and T is the thickness, so that's the volume, and is M per unit volume, and hence M is equal to AT. All right. But if I consider I, then M is IA. We know that. Okay. And hence I is equal to, so M is equal to IA and M is equal to MA, and hence I that I consider must be M into T, magnitude wise. Okay, and the surface current would be the I by T. I is per centimeter square and this is the thickness. Okay, and that is nothing but M. Okay, and hence and KB is M cross M. So that gives the direction, the magnitude. So K is simply equal to M here. Okay, so KB cross M. So notice there is no top current because M cross N are parallel. In the top, M and N are parallel. So M cross N is 0. So there is no current at the top or the bottom. Only current is there where M and N are perpendicular to each other. Okay, in this little thin slice, M cross N. All right. So, and this is K is really M in magnitude, and in direction is M cross M. So that is the physical feeling that I wanted to give you from the mathematical derivation that we did. But this was for uniformly magnetized. How about non-uniformly magnetized? Let's go and look at that. Okay, so non-uniform magnetization, that is, should give rise to a bound volume current. Let's look at that. Let's look at, it is non-uniform, then let's consider that this is the current flowing in this differential element is, since it's non-uniform, the current flowing in this direction is lots more. That's in the positive y direction. Okay, so there are two blocks, they're connected. So this current is going around like this, and this current is going around like this. This little square loops. Okay, and there's a thin, and this is in the dy direction, and M is of course is changing its function of y. It is larger here and smaller here in y, but is the which component? Is the z component. Okay, so let's look at the directions. All three directions are involved. So, so this current is going round. So if I look at this interface where I pointed out, okay, this is a small current going in this direction, but this is a large current going in positive x direction. So if I look at this interface, there's a large current coming from inside on this surface, and there's a small current going in this direction in this on this surface. And hence, there will be a net positive current at this interface. Okay, so so similarly, I can think of there is in the positive z direction, there is a larger current. My z plus delta is larger. This is the y component of the m is larger. And so this is going around this and this is going around this. So in this, so towards the x direction, okay, this is going in the positive x direction, a smaller amount, and is a larger amount going in the negative direction. So both these will contribute to the to an x current, okay, because of the two loops. The two loops are, okay, one is more and one is small, and so let's look at those two currents. Okay, now consider, so two adjacent chunks which meet along this face, okay, and right one along dy has just a more magnetization, okay, and hence there is a net current flowing in x direction. We have seen that, right? Because this is going to be more and this is going to be less on this face, okay. And how much is that? So I can, so mz, okay, into y plus dy, so that is the current, okay, and minus mzy into dz, right? So this is y plus dy is here, and minus y, okay, into dz. So I can, since it is differential element, I can write down as if it is the small differential element delta mz by delta y dy dz. I just cancelling it, right? So now I can divide this ix by the little small area dy dz, and that gives me my volume current, okay, in x direction as delta mz by del A. So this x component of the volume current coming from the change of the mz in the okay, in the y direction. Similarly, I can work this out exactly. Similarly, consider two adjacent up and bottom that I have just said, surround the xy face, and the magnetization we can immediately exactly similarly. There is but now this is smaller and this is larger in the y direction, and then it's a minus direction is larger, so minus my z plus dz. This is going inside, and this is coming out in the x direction, and there's a minus, and hence is minus del my by del z. So so jx is jb of the x component is minus del y by del mz. So in the net, in the x direction, the current, the bound current x direction, because of the non-uniformity of the magnetization, is going to be, okay, is going to be jbx del mz by del y from here, and from here del my by del mz. So this way I can work out the volume current for in all the three directions if there is non-uniformity, because, okay, and hence that will give rise to this nothing but j del cross n. That's the physical feel for the maths that we did 2 slides before. Also note that this JB, is there a divergence? Of course, divergence of any curl is zero. So note that divergence JB is zero because it's a divergence of a curl. That we know divergence of any curl is by mathematics itself is zero. So I've given you a feeling for the origin of the bound surface current and a bound volume current. Okay, where does it come from and how it is relate to almost quantitatively with, so this is heuristics, okay, but it gives you the feel. All right, so let's take an example, simple example. This is the most common example of a magnetic field of a uniformly magnetized sphere of radius r. Okay, so this is a sphere of radius r. the magnetization is along the Z uniformly, Z direction, and we are looking at what is its magnetic field everywhere because of that, right? So it's a magnetized object. The first thing is to look for what are its bound currents corresponding to, okay? So that we can find out from the bound current. So the bound current, of course, is uniformly magnetized. So del cross M is zero, okay, because of uniformity. And then KB is, of course, M cross N. And what is M? M is pointing in the K direction, and the surface here is in the R direction. N is in the R direction. So K cross R is nothing but sine theta, and in the phi direction, right? So M sine theta phi. Now, does that look familiar? M sine theta in the phi direction. Okay. Have we come across this current density earlier? We have, and that is a spinning uniformly charged shell with surface charge density sigma is spinning with omega around the k axis will give the same current. Same sigma omega r, okay, omega is in the k direction, r is in this direction. So k cross r is going to give you phi, sine theta phi, sigma omega r. So now compare this and this. So if you say M is same as sigma omega r, then all the results of the spinning charge cell can be taken directly. And we have done that in quite great detail. Okay. And what was the result? Result was if we identify M sigma omega r, the magnetic field would be identical to the spinning charge shell we have said. And for inside, of course, it will be a constant, okay, 2/3 mu naught m. This was 2/3 mu naught k. Instead of k, we have just said m, okay. It was for a current which was m sine theta phi. And outside, this like whole thing is like outside, for outside magnetic field, as if this m into the volume, as if it is a dipole at the center, okay. So that would perfectly, in fact, it's like a pure dipole. Okay. For everywhere outside, it is like a pure dipole at the center. So that is corresponding to a magnetization, magnetic dipole moment of 4 pi by 3 pi r cube into m, right? That's the total dipole moment. Okay. So m is total 4 pi by 3 pi r cube m, and that is sitting at the center. Simple. Okay. So this equivalence of the current equivalence immediately helps us to find A or B, whatever you like. Okay. So the spinning charge that we are doing, it was not merely a mathematical or a problem. This is actually a physical correspondence to a magnetized sphere. All right. So let's take another in cylindrical example. Okay, find B of a long, okay, I've taken a long, okay, means very almost infinity, uniformly magnetized circular cylinder. That was a sphere with M which is parallel to the axis. All right. So let's, this is very long and this magnetization is parallel to the axis and it is M. It's uniform. Okay. So what would be? First thing is to find out the bound currents. So it is uniform. So obviously del cross M is zero. So there is no volume current. And what is the surface current? M is in this and surface N is here in perpendicular to this curved surface. And that is S hat. Okay. So K S hat is simply M phi. Okay. So have we now come across this currents earlier? Of course we have. Okay. And that is nothing but a solenoid, a solenoidal current, K phi. Okay. It's just a solenoid current. And we know the magnetic field for a solenoid. So I can write down immediately. Hence, if we identify M as K, okay, K is the surface current of a solenoid, then there is mu naught, Ni, right? Okay. So that is B mu naught M. Okay, so Ni, you remember, okay, N turns per unit length, and I is the current, and that was gives K. And here in this case, mu naught is B is mu naught M. Okay, so because of the current which is in a phi direction, now the magnetic field is in the same direction as magnetized inside. Okay, just like in a solenoid. And outside, since it is long, outside solenoid is zero. Okay. Now, suppose it was not so long, it was a short L. I leave that as a task for you. Okay. So suppose this was not too long, but only a finite length L, then find the field on the axis, okay, like a real cylindrical magnet that you can buy at the store. Okay, so I'll leave that for you. So in the next episode, we are going to look at the uh, magnetic, the more new variables. Okay.